theory, you know, what kind of computational arrangements. The results that you got, sort of in a summarized sense. And then finally, what do they mean? What impact will it have? And we can do that in a shape that's about the same as a 4-page paper with figures, which would be about 10 pages long. And in that way, then we can give you an A is not hard to get, and we can give you a grade for the seminar. I think that actually going to at least most of the seminars, hopefully you'll find this enjoyable experience. I think it's very worthwhile. I encourage you all to do it. And if you'd like to get some help with your graduate course degrees, that works too. And let me advertise, those of you who would like to know more about this center, we have an excellent, an excellent website put together by Naomi Brave, who's the managing director of the center, which is CIQM, which is Center for Integrated Quantum Materials, .harvard.edu, and this really has a lot of information about the center. We do a variety of different activities. You might find this also interesting. Okay, any questions about the organization? Crystal clear? Excellent. Okay. So today we're going to hear a talk by a postdoc.
Graduate student.
Graduate student, DiDi Wei in Amir's group. Amir is part of the center, and he's in charge of sorry, I'm coming from Japan, and my brain is so in Japan, but topologically protected qubits for.
Okay. Thank you. Thanks for the introduction. Right, I'm a graduate student in Amir's lab. I'm working mostly with graphene, and I'm going to tell you a bit of experimental work that we've done looking at sending spin waves into a graphene quantum Hall ferromagnet. And that's what this picture is. It's an artistic representation of basically sending in spin angular momentum into a graphene puddle and having waves kind of...
Is your mic on?
I think it's on. I believe it's on. Is it good? Okay. Yeah, it's on. So this might seem kind of strange because graphene, which is this atomically thin 2D piece of graphite, is not naturally magnetic. So it seems a bit strange to do research in the magnetism of graphene. However, one of the really nice things about graphene is that you can engineer it into a lot of different very interesting phases, either by altering it physically or by putting it into specific environments such as low temperatures or high magnetic fields. So for instance, one really nice result that came just last year was basically this superconductivity result where they take two pieces of graphene, twist them on each other, and you see superconductivity. And one of the very interesting parts of this experiment is that it looks a lot like high TC superconductivity, or superconductivity that arises at high temperatures. And there's a big question of whether or not magnetism is in this system because it does play a big role in high TC superconductors. Another example is topological materials. So there's a lot of effort to engineer graphene into a topological regime, and magnetism plays a big role in all of these experiments. Specifically, the regime I'll talk about today is that of quantum Hall magnets. So this is the system that I'll be explaining and talking a bit more about today. And the way that we want to probe these quantum Hall magnets is with spin excitations. And you can think about sending a spin excitation through a magnetic material to get more information out of it, just like you can send an electrical current through, say, a metal or a semiconductor in order to probe these materials. And you can basically think about two different kinds of spin waves. So the first one is this conduction electron spin current, and essentially it's conduction electrons carry some spin, and when they move, they carry the spin with them. There's also in magnetic insulators collective motion of spins, which is this spin wave spin current, and essentially this can propagate through magnetic insulators without also carrying conduction electrons. And this is the one that I'll be focusing on mainly today, just because a lot of the really interesting magnetic states that we have in, that show up in graphene are insulating. And the reason we would want to do this is, first of all, we can just probe the magnetic ordering, which is, it answers a lot of questions in graphene, but because this is an excitation, we can also look at excited states. And eventually, if we're able to control these magnons very well, we can look for magnetic analogs to electric phenomena. So things like ballistic transport, we can look for ballistic magnons, we can look for magnonic quantum Hall effect, spin superfluidity, which is the analog to superconductivity, all kinds of analogs which can be probed in different magnetic systems. Okay, so the outline of my talk, I'll introduce the quantum Hall magnets, then I'll briefly sort of show you what our magnon generation scheme should be, or what we want to do in these quantum Hall magnets, and then I'll show you how we send them and basically all of the experimental verification we've done to show that we have magnons in our system and that we can propagate them. We'll use these magnons to probe different quantum Hall regimes, and then finally we can talk about maybe using these magnons in different graphene systems as an experimental probe. So first, just to introduce quantum Hall magnets, so to introduce graphene, graphene is made of, like I said, these carbon atoms, which are in this honeycomb lattice made of an inequivalent A and B sublattices. If you look at the electronic band structure in the 6 corners of the Brion zone, we have these inequivalent K and K prime points, which we call valley. And these points are particularly important for electronic transport because they're at low energy, so all of the low energy excitations that we use probe really these K and K prime points. So if we put our graphene into low temperatures and high magnetic field, we get a quantization of the energy levels, which in a real system are confined in a confining potential. And if you look at it with respect to position and energy, you get a curving of these quantized energy levels. And what we can do is tune the Fermi level, which is basically a measure of sort of the densities in the system. And we can do this very easily in graphene with just a gate that's nearby, a metal gate. And the places at which the Fermi level crosses these energy levels, we get 1D ballistic edge states. So looking top down at a device, so in the quantum Hall regime, for instance, if we filled 3 Landau levels, which we call nu equals 3, then we have 3 edge states along the boundaries of the device, and we have an insulating bulk. And each edge state contributes E squared over h of conductance. So if we look at experimentally what the quantum Hall effect looks like, particularly in graphene, we see that in 2005 they found these quantized Hall plateaus. So here's an image of the device that they used to look at the quantum Hall effect, and here's a plot with respect to density, or basically how many carriers are in the system. On this axis we have the Hall conductance in units of 4 e squared over h. And they're in 4 e squared over h because we have a 2-fold symmetry from spin and a 2-fold symmetry from valley. And you can see that at each 4-fold integer that we have this quantized Hall plateau, which indicates that it's in one of these energy gaps. And you can see on the left-hand side the rho xx, which is the resistivity, the longitudinal resistivity, which shows it going to 0 at each of these quantum Hall plateaus. And basically that indicates that you have this 1D ballistic edge states, which is connecting these 2 leads together. So if you go to higher field, you can actually break this 4-fold symmetry. And here's some data that is from our group, but this was first seen in 2006 by Zhang et al. And so in low field at 3 Tesla, you see again that we have this 4-fold degeneracy. When you look at, again, this is the back gate, but it's just a measure of the density in the system and conductance. And if you go up to higher field, you can see that now we have plateaus at every integer, and this is basically the symmetry is breaking, and now we have polarized states. And you can think of this in terms of basic ferromagnetism. So if we have, essentially, you can think of it as electrons sort of don't like to be next to each other. So if we can make their orbital wave function antisymmetric, then this will give us a lower ground state. So essentially, when we have a spin polarized state, so all the spins are polarized up, for instance, this is a lower ground state, lower energy ground state than no polarization. So spontaneously, the system would like to be in this completely spin polarized state. And although this process is spontaneous, we do have some anisotropies in the system that we have to think about. So here is a basic energy plot of the different competing energies in the system with respect to perpendicular magnetic field. And essentially what this shows is that the cyclotron energy, or the distance between the Landau levels and the Coulomb energy, which is what I just mentioned, are quite large and are responsible for quantum Hall ferromagnetism, but there are also anisotropies in the system. Particularly, the simplest to think about is the Zeeman energy, which is just aligning with magnetic field, and then short-range interactions, which dictate which valley is favored. And this comes from a combination of electron-electron interactions and electron-phonon interactions. And so the experimental work that was done to sort of determine what kind of spin polarization and valley polarization in the system was done in 2012, and they looked at activation energy. So if you have, for instance, dominant spin anisotropy, you would expect sort of this energy splitting to be larger, and so you would get an alternating K prime K filling of your Landau levels. Alternatively, if you have a larger valley splitting, then you would get this alternative spin up, spin down filling. And so this is what they found in 2012. And this is going to be important to know that if you sequentially fill in the n equals 0 Landau level, you'll get oppositely spin polarized levels. So now we have our quantum Hall ferromagnet, and we want to basically send some spin waves through to probe the system. And maybe before I talk about sending spin waves in graphene, I could mention just how people generally send spin waves through 3D magnetic insulators. So the ability to send spin waves through magnetic insulators is itself a little new. So the first results came out in 2010. And essentially what people do is they couple metal with large spin orbit coupling, such as platinum, to a ferromagnetic insulator like YIG, or some sort of magnetic insulator. And they send a large current through, which through the spin Hall effect generates a large spin imbalance in the magnetic insulator. This causes a spin wave to travel through the insulator, and on the other side, an inverse effect happens, the inverse spin Hall effect, where this imbalance of spin potential basically generates a large voltage. So they can generate and detect spin waves via transport. Yeah? Mm-hmm.
Could you say what the gray part, the pink?
Yeah, sorry. So the platinum is shown in this light gray. This blue here is just a magnetic insulator. In this case, in these papers, it's YIG. So far this has only been shown in YIG or variants of YIG. And I think this purple layer is just some substrate that the YIG has been grown on.
So those are spin waves.
Yeah, these like yellow guys are spin waves going through. Yeah.
What's the length that these spin waves can transfer?
Yeah, so I think the most recent results that I know of for probing the distance is around 40 microns. Yeah, so it's pretty long distance transport. Yeah, spin wave transport. Right. So essentially, we want to achieve this basically in a 2D system. So there are a number of experimental difficulties. Like I mentioned, it's only been achieved in YIG because this interface is very important and it's kind of tricky to get right. Additionally, we have to send pretty large currents through, which would probably destroy all of the interesting magnetic phases that we want to look at in graphene. So the plan is to sort of adapt this scheme for our quantum Hall ferromagnet. And our general plan, or what we'd like to do, is essentially to flip spins at the edges, because these are our conducting edge states, and generate this and transfer the spin angular momentum into the bulk as magnons. And there are a couple of experimental difficulties to this general scheme. So first of all, how do we get two edge states with opposite spin next to each other? That's something we have to solve. How do we get electrons of one spin to scatter into another edge state? How do we generate these spin flips? And then once we have magnons in the bulk, how do we detect these magnons? Because ideally, we'd like to just detect it with transport as well. We don't want to have to bring in like an external magnetic probe, because that's just more difficult. So it turns out that really these first two things are pretty easy in terms of just making devices in graphene. So to solve the problem of how do we get two edge states next to each other, if we start out with our quantum Hall ferromagnet that's, for instance, completely spin polarized up with these conducting edge states, one really nice thing about graphene is that, like I said, you can tune it very, very easily. So all you have to do is put in an external gate. Like we talked about with the band structure, in graphene, as you fill the n=0 Landau level, you get these opposite spin polarizations for your edge states. So if we have our real device, which I show here, here we have the graphene, which is outlined in black, and the graphene is sort of sandwiched in between two pieces of boron nitride, which just act as an inert substrate to keep it clean and also to act as a dielectric. These sort of orange parts here are the leads to the graphene, and the yellow part on top is the top gate. So this is a very simple device, and essentially what is really nice is that we can just use this top gate and the sort of global gate, which is just like a piece of metal that we have at the bottom, to tune these different parts of the graphene into different regions. So we can tune this top gate region into a different filling factor than these outside regions. Basically what we can get is in the central region, we can have n=1, but then we can bring in another edge state in n=2, for instance, that has an opposite spin. Okay, so we've solved this problem of how do we get these two edge states next to each other. And then we have the problem of how do we scatter between two different edge states. And just to give a brief introduction to transport in the quantum Hall regime, what we generally do is we put a small AC excitation onto our device. So we have some higher chemical potential over here, some lower chemical potential over here, which I just called a hot edge and a cold edge. And what happens is that these quantum Hall edges are coupled to the reservoirs from which they originate. So we have a hot edge over here and a cold edge over here, and the voltage drop actually occurs sort of at these hot spots right here. And there's a really nice experiment that was done in 1991 that looked at quantum Hall in gallium arsenide in liquid helium. And what they showed was that indeed there are these points of basically heat dissipation where all of the voltage drop is indeed happening. So anyways, just in like a two-terminal measurement, just a regular two-terminal measurement we kind of get this automatically getting two edge states of different energies next to each other. So here's our system that we've gated into different filling factors. And what we do is just what we normally do with transport, which is to apply a bias. And we find that we get these regions where we have a hot edge next to a cold edge. And what that gives us is basically a higher energy state next to a lower energy state. And what they would like to do is to basically come to the same energy or equilibrate, as the terminology is. So right, ideally what we would like is for, we're trying to cause spin flips to happen so we can have this hot edge of spin down next to this cold edge of spin up, and we would expect them to equilibrate. So just one more thing to note about transport is that it's a little difficult to see it in this particular schematic, because even if these two edge states were to equilibrate or to scatter into each other, it'd be difficult to tell or impossible to tell because these two edge states are going into the same contact, this one over here. So we would need a slightly different configuration, and we have done these experiments, and people have done them in the past, and they've also been done in gallium arsenide, where basically if you have just the opposite of this, so instead of 2, 1, 2, you have 1, 2, 1 filling factors, and you send in an edge state which can scatter into this oppositely spin polarized edge state. It can now backscatter, and it can change the conductance. However, people have seen, and we've also seen, that this process basically doesn't happen. So these edges are essentially spin protected from each other, and there's no scattering of spins. And the reason for this, which we thought about for a little bit, and then realized that there is basically a minimum energy to create a magnon in the system. So essentially, the system would like to generate some spin angular momentum by scattering these two spins. However, they are unable to because there's nowhere for that spin angular momentum to go. So in theory, right, the Zeeman energy is the minimum that is required. And so this is something that's pretty easily overcome in experiments as well, because what we can do is basically put a larger DC bias onto the system. So we have our small AC excitation. Yeah.
With the graphene, how am I supposed to think about the magnon like a gig? The spins are not moving anywhere, so that they couple to each other like a ferromagnet. Spins are lined up and they twist it, and then you get a spin wave.
Yeah.
In the graphene, the electrons are highly mobile each other. And so it's a quantum Hall effect going to insulating regime between the edge states and insulating.
Yeah, so ideally, so ideally the magnons are just propagating in the insulating bulk of the quantum Hall ferromagnet and not at the conducting edges.
But they're insulating because they're going around in closed loops, cyclotron orbits that go nowhere.
Yeah, but they still have some sort of spin polarization.
Sure.
And it's basically the same with YIG. So it's like one is kind of like tilted with respect to the other. You change the spin polarization of each sequentially until you get a collective motion of magnetic moment through your system.
The quantum Hall effect is essential because that's what makes it an insulator.
Yeah, and also it gives us these edge states where we can do the spin scattering. Yeah. So in this system, what we expect to happen is, so now we have our hot edge of one spin next to a cold edge of another spin. We apply a larger DC bias, and what we expect to happen is that once we exceed the Zeeman energy, we should expect to see some spin flips happen at this corner. And from that spin flip, we expect the magnons to be created in this insulating phase, denoted by this minus sign here, because just an experimental detail is that the chemical potential is the negative of the actual bias that we're applying. So in experimental data, you'll see that magnons are generated here in negative bias. And you, again, might have trouble seeing this because, again, if we create a magnon here, then these two edge states will equilibrate, but they end up going into the same contact. So what we need is sort of some inverse effect to happen, just like in 3D, sending spin waves through 3D materials. We need some sort of inverse spin Hall effect. And so, and that's how we detect that we've generated spin waves. And so what we'd like is basically for this inverse effect where we absorb a magnon and flip a spin into a different edge state. And this will actually alter the chemical potential between two edge states, and we should detect that in a conductance measurement.
There's some nice experiments. Again, sorry.
No, it's fine.
Japan did, where he saw these hotspots because he met actually far infrared radiation energies that you're talking about. And
Sorry, who did these experiments? Oh.
Sorry, it'll come to me in about 20 minutes or something like that. But this was about 10 years ago, but he was a very clever guy. He used another piece of gallium arsenide as far infrared detector, but it wasn't physically connected. So he was doing it in the far infrared, not in magnons. But actually worked. And we think
Cool. Yeah, maybe I can.
I'll show you.
Get that paper from you. Yeah.
Could be.
Yeah, I'm not familiar. Yeah, I'll look for that result. Okay, so you might also ask, though, there's another point of a hot edge next to a cold edge here, and why aren't magnons generated there? And the reason is because if you look at the entire system, we basically have a spin-up polarized ferromagnet. And when we put in spin-down angular momentum, or if we flip from a down to an up spin, we can generate a magnon in the system. But we can't go the other way because we can't basically put more up spin into this completely spin-polarized ferromagnet. However, if we simply switch the sign of the bias, so now if we go to positive bias, we're essentially switching the hot and the cold edges, and now we can generate magnons in this corner as well. So we can do it for both signs of bias. Okay, so let's look at some actual experimental data. So if we, so I think my device is gone, but if we have our device where we basically have the hot edges and the cold edges here, and we have our chemical potential, hot chemical potential, low chemical potential, and we look essentially below the Zeeman energy, we expect to get something where we expect to get a quantized conductance at 1e²/h. So that's what we see in our experiments. And if we go to, for instance, negative bias, what we expect is now for magnons to be generated in this corner here and to propagate across the device and to change the conductance of the system. And so once we do that, we indeed see that there's a change in the conductance in the system right at the Zeeman energy. And again, for positive bias, where we expect magnons also generated just in a different corner of the device, once we exceed the Zeeman energy, we also see a change in conductance. So I think my actual device is here, but basically this sort of confirms our picture that at the Zeeman energy, we're doing something to the system where now we can see spin flips. Okay, so this is kind of just like a preliminary, some preliminary data for what we saw at first. And next, I sort of like to really convince you that what we see is magnon generation and also detection. So the first experiment, yeah, yeah. Here, oh, so it depends on the magnetic field. So here, I think this is around 4 Tesla. Yeah, and the Zeeman energy is the ground.
So that matches that value that you see there with BDC matches your Zeeman energy?
Yeah, yeah.
So then I guess if you have this magnetic field dependence, you can see that you need more voltage to inject magnetism.
Yeah, you're asking about magnetic field dependence of the like breakdown.
Right.
Yeah, so if we do, we did tilted field measurements. So basically, because everything like the cyclotron energy and the Coulomb energy, they all depend on perpendicular magnetic field, but the only thing that really depends on parallel magnetic field is the Zeeman energy. So we put it in a tilted field in order to hopefully see that it's linear with the total magnetic field and not with, say, perpendicular magnetic field. So what we, yeah.
Why not the conductance decrease magnon?
Yeah, so I didn't go over that. That's the detail I didn't mention, what happens if the conductance should go down or go up. But I will hopefully address that question soon. Yeah. So here, if we just plot the Zeeman energy with this graph, we see that indeed it scales linearly with the total magnetic field, or this drop-off scales linearly with the total magnetic field. And to see this more clearly, we saturated the color scale and see that this like sharp cutoff really happens with total field.
Why there is a symmetry?
In the conductance? Yeah, it has to do with the geometry of the device, which I will hopefully show you in just a couple slides. And just as an experimental note, this is a very easy experiment to replicate because we don't actually need to gate these sort of nu=2 regions out here because we actually get it for free just from contact doping from our contacts. So when you contact graphene with some sort of metal, it brings this sort of edge area into a higher chemical potential. Essentially what we get is it's probably not nu=2, but it's some higher doping, which gives us opposite spin edge states at the borders. And so this is just a 2-terminal measurement of any piece of graphene should give you, if you look at the bias dependence, you should have a breakdown at the Zeeman energy in nu=1. Okay, so so what happens exactly at the Zeeman energy to the conductance? Something that we did was this distance dependence because we actually wanted to see how magnons travel across the device and what they're actually doing to the conductance in the device. So what we can do with this experiment is sort of to take it piece by piece and look at different geometries and how the magnons are traveling. So if we just look into this region over here, again, we can do our simple 2-terminal measurement. And in our experimental data, what we see is, again, if we're looking at the DC bias and we're looking at the conductance just between, as two terminal between these two contacts, we see quantized conductance of 1 e²/h. And if you want to think about what is actually happening in the system, the details, magnons are again being generated at this place where at negative bias, and they're absorbed at this point over here and this point over here. And they do different things to the conductance. So say I call this one epsilon 1. If spins are scattered here, then they're essentially backscattered into the originating contact, and that should decrease the conductance in your system. Over here at epsilon 2, if spins are scattered, they're forward scattering into the drain contact, and that should actually increase the amount of conductance in your system. So in this chart here, for this negative bias, what we see is that for epsilon 1 causes decrease, epsilon 2 causes conductance increase. And if these processes are equal, then we wouldn't see anything at all at the Zeeman energy. But if we make a naive assumption that essentially a spot of magnon absorption, if it's closer to magnon generation, then it should have more of an effect than a faraway point. Then we can see from this schematic that essentially epsilon 1 should have a much bigger impact than epsilon 2. And you can also see it in the optical image. This point is just closer than epsilon 2. So we expect conductance decrease for negative bias. And in our experimental data, we see, in fact, that at negative bias, we can, like in the previous device, we see a decrease in the conductance. We can also look at positive bias. And in this case, again, we have that epsilon 1 is closer to magnon generation than epsilon 2. But in this case, you can see that because the hot and the cold edges have reversed, now we have forward scattering at epsilon 1, which should increase the conductance. So we actually expect an increase in the conductance for positive bias. And in this geometry, we again see that indeed the conductance increases once we hit the Zeeman energy. So you can do this kind of calculation for for a number of different geometries in this device, which is what we've done. So I won't go over sort of the thought process in each one because it gets quite tedious. But for different geometries, basically moving epsilon 1 and epsilon 2 or placing them further or closer to points of magnon generation, we can get that the conductance decreases on both sides or increases on both sides or is asymmetric. And it all follows with the geometry of the device. And this also sort of confirms that magnons are indeed traveling through the device. They're just absorbed at places that are closer and not so much at places that are far away. Okay, so the sort of final conclusive experiment we did was this non-local magnon signal. So there are a number of reasons why you'd want to do a non-local signal, which is basically you want to generate something at some location and detect it far away. And this is sort of better proof that you're generating magnons, partly because you should be draining all of the current away at one of these leads over here. So you should source voltage drain just like the two terminal conductance measurements we've been doing this whole time. And so you shouldn't be transporting any current. In those previous experiments, we're transporting current and a magnetic signal at the same time. So things can get jumbled up. But here in a non-local measurement, you should just be getting a voltage signal from magnons that are propagating through and without any charge current. The other nice thing is that you can basically have a top gate and tune some region of your device into different quantum Hall filling factors. So we can tune it into ferromagnets, nu equals -1, nu equals 1. Non-magnetic regime, this nu equals 2 area, or we can tune it into something interesting, which is this nu equals 0 canted antiferromagnet, which I will talk about in a couple slides. So just to look at the whole set of data through all of these quantum Hall phases, what we can do is tune this top gate. So we can just change this top gate so that it runs through all of these filling factors. And we can change the DC bias so that at some point, here's the Zeeman energy. You can see that at some point this signal turns on. And that's when we're really sending magnons through our system. So for -2 and 2, which are non-magnetic, you can see that the signal is suppressed. At -1 and 1, we see that we have a strong signal, which is asymmetric, which is what we expect from the geometry of our device. And at nu equals 0, in this plot, we see nothing, we see that the signal is heavily suppressed, which is quite disappointing because the nu equals 0 regime in quantum Hall in graphene is quite interesting. So if I could just take a small detour to talk about nu equals 0, basically in the experimental regime, you have a half-filled Landau level, which basically means that you have K and spin, and the exact ground state of this system is complicated and is determined by electron-electron interactions and electron-phonon interactions. And experimentally, this is seen first by Joe Chikelsky in 2008. What people see is this nu equals 0 plateau in gate voltage and conductance, Hall conductance. And they see that in RxX, this state becomes extremely insulating. Just phenomenologically, this is an extremely insulating state, and there was a lot of debate theoretically as to what the ground state was. So there was a lot of theory prior to this, but in 2012, Kharitonov basically came up with this big phase diagram for the different states, ground states of nu equals 0. So we have a Kekulé disorder, a charge density wave, a canted antiferromagnet. The most interesting thing that experimentally that came out of this theory paper was essentially that you could tune from one of these phases into a ferromagnet with an applied parallel field. So if you follow this arrow, you can just tune from the canted antiferromagnet to a ferromagnet. And people have done this in experiments. So in 2014, at MIT, they did this experiment where they basically apply a large parallel field at very high fields. And you can tune from this very insulating nu equals 0 state. So this is, again, the gate voltage and the conductance. They can tune from this very insulating nu equals 0 state to this ferromagnet state, which has 2 counterpropagating edge states, which they call a quantum spin Hall state. And this quantum spin Hall state is very interesting in itself, but another thing that this paper did was basically sort of show that the ground state of nu equals 0 in graphene is a canted antiferromagnet. And since then, a lot of theory papers have come out, particularly ones which propose that spin superfluidity could exist in this nu equals 0 phase. And basically, that's a magnetic analog of superconductivity in graphene. So, right, so in our experiment, we were quite disappointed because we don't really see any magnetic signatures in this nu equals 0 regime. We talked to our theory collaborator, Bart Halperin, and he suggested essentially that's because of the interface between nu equals 1 and nu equals 0. So here we have an energy diagram with respect to position. On one side, we have our nu equals 1 ferromagnet, and then it has an interface with nu equals 0. And what we're trying to do is basically generate magnons in nu equals 1 and send them through nu equals 0. And possibly what happens at the interface is that the spins in the canted antiferromagnet get pinned to the spins in nu equals 1. And basically, they're sort of rigid and can't propagate magnons through this particular interface, depending on the potential or how high or how large the interface is. So in an energy diagram, this looks like at nu equals 1, we have the Zeeman energy, which is the minimum energy to generate a magnon. And then in the canted antiferromagnet, basically they should be able to theoretically propagate through at 0 energy. And at the interface, we have this sort of larger energy barrier that we have not overcome in our data. So what we did, so this is also something that we can overcome experimentally by simply looking at this region, sort of the nu equals 0 region we have here, and increasing the DC bias, so increasing the energy that we need to go to in order to surpass this barrier. So that's what we did. We looked at that region and we went to much higher DC biases. So again, this is with a top gate, but this is just in this very small region here at much higher biases. And what we see is these signals at high bias, which indicate that now we're surpassing this this energy barrier. And if you have an energy barrier, you should also perhaps be able to tunnel magnons through the system. So if we look at this, this signal here, so this is just an average of these vertical line cuts, we should see that at very low energies, we might expect to see some tunneling signature going through this barrier here. And so if we look there, we indeed see small signatures of something going through right at the Zeeman energy, which we interpret as a tunneling signature. So this is sort of the first experimental verification of magnetism in a canted antiferromagnet. And yeah, so ideally what we would like to do is sort of extend this to different quantum Hall systems that are also interesting in graphene. Okay, so that sort of brings me to my final bit, which is what are the experimental possibilities to use magnons as probes in this system? So first of all, spin superfluidity is still something that people are looking for in this system and in general. So what ideally you would like to see is no decrease in signal over long distances and signals beginning at very low excitations. So in ours, we can only basically see signals that start at the Zeeman energy because we're generating them in nu equals 1 and sending them through the nu equals 0 ferromagnet. In this theory paper, they propose just generating magnons directly in the nu equals 0 canted antiferromagnet, and those should start at very low excitation energies. So this was this basic schematic was done in Peter Stepanov's paper in 2018, where they basically tried to generate magnons directly at nu equals 0, but like in our paper, the signal doesn't really start until you reach higher biases. So I think it's still very much an open question of whether spin superfluidity exists in this system. Next, there's also a lot of different fractional quantum Hall phases where people see these strange phase transitions at different fractional regimes. So this is from 2013 from our group. This is from Zeeman in just this past year as well. And essentially, there are these phase transitions which people are not sure of whether they include changes in spin polarization or not. So ideally, what we could do is look at if there's a Magnon signal through some of these phases and then see it either appear or disappear once we go through this phase transition. Okay, and then finally, like I mentioned in the introduction, there's a lot of different exciting physics going on in twisted structures right now. And we can use this as sort of just a general probe of magnetism in graphene. So for instance, what we can do here is generate magnons in sort of a quantum Hall phase of monolayer graphene, see if it propagates through twisted bilayer graphene, and then detect it on the other side. And all this requires is essentially interesting phases that survive up to the sort of fields that we need to see quantum Hall ferromagnetism, which is about 1 Tesla. So yeah, so this experiment here shows that with density, the densities at which these interesting magnetic insulating phase, or these interesting insulating phases occur, they survive up to quite high magnetic field. And I think it's still a big question of whether there's any sort of magnetism apparent in these systems. So yeah, so in general, I think it would just be a nice sort of probe of the different kinds of magnetism in different graphene structures. Okay, so I just wanted to thank all of the people who worked on this with me. So Tuna van der Sar, who is now professor at Delft, and Sung-Hong Lee, who contributed a lot to the project. Amir and Bert were behind a lot of the ideas and just generally helping us figure out all of the data in the system. In the Kim group, we used all of their fabrication, their transfer setup to make all of our devices, and our collaborators at NIMS grew all of our boron nitride. So yeah, so thank you for listening.
Let's see, questions?
Magnons are generated only on the hotspots or in all corners of the device?
So in right, in like the devices that I showed, so our theory is that they are only generated at these like corners where, yeah. So like for negative bias, for instance, they're only generated. We think they're only generated like right here, basically.
That's a hotspot, right?
Yeah. Mm-hmm.
What about their absorption? Absorption happens also only on the hotspot, or in all?
No, it should happen. We think everywhere. So like here, it happens here, but we just don't care about it because if there's any sort of chemical potential redistribution here, they end up going to the same contact. So effectively, it happens in all other corners, but we only care about like these two.
Is it possible to explain this asymmetry? Like it is absorbed everywhere, but it is generated only on the hotspot?
You mean the asymmetry in the like value of conductance that we see?
Like the generation is, let's say, only on 2 spots, but absorption is in 4 spots.
Yeah, but sorry, what asymmetry are you talking about?
So basically, there are more absorption spots than generation spots.
Yeah,
or am I wrong?
No, that's true. Yeah.
Is it possible to explain that, or?
Oh, just why there are more absorption spots than?
Yeah.
Oh, yeah. So so there's only one place that spin flips are allowed in this system. Like, so if you just take this for instance, we need a down spin to flip to an up spin state because that's the only kind of angular momentum that this system can absorb. And the only place where you have like a hot edge next to a cold edge, the hot edge being down spin and the cold edge being up spin, is at this corner here. So there's only one spot.
To generate.
Yeah.
To absorb, it's different.
Yeah, to absorb, there's, you can think of it as like it's a continuous pumping of sort of magnons in the system. And even if they're at the same chemical potential, they absorb the magnon and then they shift chemical potential so they can absorb anywhere. Yeah.
And that spin flip is generated due to let's say equilibration, this hotspot, or
you have to go through the quantum Hall boundary conditions. The quantum Hall effect. They don't allow you to have a hotspot except for a quick time. Other questions?
I may have just missed it, but what is the characteristic length scale at which a non-local signal is dying?
Oh, so we haven't, basically we're limited by device fabrication, so we haven't made a device long enough where we see the signal die out. So the longest devices we've made is like 10 microns, so we know that it propagates over. Yeah, yeah, and
you are doing this kind of DVDI oscillation measurements at low frequencies, or it's all DC kind of measurements?
Yeah, we're just applying a DC voltage. Yeah, so we think that it could propagate over very long distances because there's nothing to really scatter because there's low spin orbit in the system. But again, we're just we just can't make.
So across the whole device, the signal is just the same?
Well, so the signal the signal that we get is a combination of so like in some corners it increases the conductance, in some corners it decreases the conductance, for instance. So it's sort of like we can't get an absolute value, but in terms of like seeing a signal, we see it across however large we can make the device. Yeah.
So these are some of these plots where, as you change the bias, you get the Zeeman energy, the conductance either goes up or down, but then it kind of recovers back to the initial value. Why does it come back? Yeah,
that's a really good question. So we actually have no idea really what is happening. You're talking about like here, for instance, like what happens right here. Yeah, so we don't really know what happens after you exceed the Zeeman energy. So, right, so all of this is basically what happens at the Zeeman energy and where are the magnons going, and I think that we understand quite well, but once you get into higher biases, there could be like effects from heating or something else strange that we don't know. It's also possible that you're just not generating magnons there anymore. You've hit the like magnon bandwidth, and you're just not. It's recovered because you're not doing anything there anymore. I think, yeah, that's something that we would definitely like to know, but we're not sure of. Mm-hmm.
Ask another one. Yeah. Thank you. I'm just wondering, like, so all this is sort of transport measurements. But
Yeah.
Is there any kind of experimental approach, like similar to emission of radiation, which you can apply to say that, like, this sort of signal which we're seeing is due to magnons, like noise measurements? Can you see anything in noise, or what can you?
I don't know about noise measurements, but yeah, I mean, definitely this is something that I think that we would like to see with an external magnetic probe. But so it's just kind of a challenge to get one of those, you know, at low temperatures and high magnetic fields. But for instance, like MV probes or like a scanning nanosquid, I think, or even just like a thermal measurement, it's possible that there's, you know, a lot of heat generated. Yeah, when the equilibration happens. So. Yeah, so I think there are measurements that can be done, but I think it's maybe challenging because, yeah, because of a quantum Hall system. So,
Okay, one last question.
So for the nucleus here, where you show that there is this, where you say that there might be magnons for nucleus here, right? But that was in the non-local measurement. So
this one?
Right.
Yeah. Yeah.
I mean, that requires definitely more voltage, so where it might be prone to more of, phono generation.
Yeah.
Right? So you might be taking the sample.
Yes.
So do you have this also in the local measurement? And
so we can't do this in the local measurement because we have to generate in nucleus 1 and then propagate them through nucleus 0. So yeah, so we can't just do like a 2-terminal measurement. But that's a really good point. In like this bias is quite high. So we've also, since then, we've seen, we've measured more devices where this bias is much lower, so there's a much less chance of having like heating be a factor. And also, when we take these measurements, we also definitely measure the leakage current on the, so in our device, what we have is like we have another contact, say over here. So we're generating magnons, and then we measure the leakage current on the other side. And even though we're at high biases, we still see nothing in terms of, yeah, like electrical transport across this region.
yeah, but, I mean, you might be just generating a hotspot in terms of Joule heating on the lead 1 and lead 2, right? When you're doing that.
Yeah, but since we're measuring a non-local voltage just on the other side, even if we are applying high biases on this side, yeah, so we're not measuring anything current-wise that's coming across.
Okay, well, let's thank our speaker again. All right, and people who are taking it for a course, please come down and sign in. I say if somebody is interested in taking it, this semester that didn't do it